Thank you very much for inviting me, for giving me the chance to talk about this highly multidisciplinary project. So before I start, I want to recognize my colleagues on this. Nancy Soros on the top right is the material scientist of the team, especially on the experimental assessment and the manufacturing process. Jeff Moore in the middle is the chemist of the team. He's an expert in organic chemistry. And then I also want to recognize the contribution of our colleague, Scott White, who unfortunately passed away a couple of years ago, but was a major force behind the start of this project and the inspiration behind this. So this project was supported by the Air Force Office of Scientific Research and the National Science Foundation. It is taking place in a multidisciplinary group at the Beckman Institute called the Autonomous Material Systems Group. And you have here some of the pictures of the pictures of some of the participants, students and postdocs involved in this project. So I'm going to talk about the manufacturing of thermoset composites, right? So these are increasingly used in a wide set or wide range of applications. Obviously, from aerospace industry, that's the thing that industry that is dear to my heart. With both military aircraft, but also commercial aircraft, and you have at the bottom the part of composites in a 787, but also in the wind industry, in construction, in some of car manufacturing, and in sport type of equipment. The challenge of widening the application of composites is due to the fact that manufacturing these composites is very challenging and costly, especially if you want to make very big parts, like if you want to make part of the fuselage or part of the wing of an airliner, right? You have to use these very large autoclaves. And so here's a picture of one of them for the 777. You can see the size of a human right over here, right? Or if you want to make the wind turbine blades, you have to use these very, very large heating molds. And so what we would like to do is to really speed up the process and reduce the cost and complexity of it. And the challenges are due to the fact that in these autoclaves, these materials are subjected to fairly complex temperature and pressure profiles. So the temperature profile here as a function of time in hours, right? The red curve corresponds to the temperature profile, the blue one corresponds to the pressure. And these have been developed over the years due to the various limitations of the process, right? So it's a low thermal conductivity of the thermoset polymer. So therefore you have to use a low heat to heat abrade. You want to make sure that you have a uniform curing of the part. So that complicates, obviously, the control of the temperature environment inside these autoclaves. And obviously, there's a very large capital investment and operating expense of these autoclaves. And obviously, there's a limited availability of these, and obviously generate a lot of CO2 in the process. So that has led some researchers who wrote a review on manufacturing processes of these thermoset composites to conclude that the autoclave curing process, which is widely used for curing of high-performance fiber-reinforced polymer composites, is labor and capital intensive, with costs increasing exponentially with part size. So what we are trying to do with this particular project is to change the paradigm a little bit about how these materials are actually made. And so what we kind of displayed this in a kind of a schematic form of showing, on the y-axis is the energy consumed per volume, on the x-axis this is time to cure per volume. The 787 will be up here, right? It takes multiple hours in an autoclave to make these very, very large parts. What we want to do is to reduce it and bring it over here. That's the objective. The dark symbols over here are parts that we've already made. Obviously, we haven't made a 787 at this point, but the objective is really to reduce the time to cure by about 2 orders of magnitude. So go from hours to minutes to reduce the energy consumption by many orders of magnitude. Whether it's 3, 4, 5, 6, or even more, that would make a major difference. And obviously, in doing so, we would substantially reduce the capital investment because we want to make this out of an autoclave and reduce the CO2 emission as well. So the approach that we've adopted is based on the concept of frontal polymerization. And so to schematically illustrate what it is, the idea is to put a latent catalyst in a monomer to introduce a thermal trigger that activates the catalyst and start a chemical reaction. It's an exothermic polymerization, and therefore what happens is that the reaction, the heat of reaction polymerizes the material, but also heats up the material ahead of it, activating the catalyst, and eventually the thing propagates as a wave, right? We did not invent frontal polymerization. Actually, it's been around for a while. It's been discovered in the 60s in what was the Soviet Union at that time, is Russia now. And it's been observed in a wide variety of polymer systems. We've looked at a few of them. The one that I will emphasize in my presentation today is dicyclopentadiene. So this is the monomer, and this is the representation of the polymer. And it can be triggered in different ways, right? It can be most of what we do is thermal, but we've also done photo or chemical trigger. And the key requirements to have frontal polymerization is you have to have a low rate of reaction at initial temperature, so you can go through the manufacturing process, set up the part that you want to make, and then once you introduce the trigger, you want to have a very high rate of exothermic reaction at higher temperature in such a way that the rate of heat production greatly exceeds the rate of heat loss. And for those who are interested, I recommend a very nice review paper by John Poyman, who's at LSU, Louisiana State University, in polymer science in 2012. So the best way to visualize what frontal polymerization is to look at this video. So imagine you have a little part, right? It's 10 by 10 centimeter. And then what we did is we actually introduced a wire in there to introduce the thermal trigger. And so if you run the current for just a little bit, just to get it started, you can see a front that propagates. And it's a very sharp front. Ahead of the front, you have a liquid monomer, right, DCPD, that has a viscosity of water. Behind the front, you have a fully polymerized polymer. And the idea is that we can actually cure this part in 78 seconds with just 6 joules of energy. So this is kind of illustration of what frontal polymerization is about. I will emphasize the modeling aspect in this presentation, and it's important to realize how the basic equation that characterized this process, and it's simply based on the reaction-diffusion model. It's been around for a while. It's written in terms of the temperature solution and alpha, which is the degree of cure. So the degree of cure is 0 when it's a monomer, it's 1 when it's a fully polymerized polymer, right? And then the key quantities you have here are the thermal conductivity, the density. HR is the heat of reaction. So that's the amount of heat that is created by the exothermic reaction, right? And you have a term that is proportional to the evolution of the degree of cure, which is itself characterized by the second equation, which is a cure kinetic model. So the A is the pre-exponential constant, E is in the activation energy, and the coefficients that show up in the second equation are typically obtained through an experiment called the differential scanning calorimetry type of experiment. So from a purely theoretical point of view, the challenge is obviously it's a multi-physics coupled type of equation. You have to solve for both temperature and degree of cure. It's non-linear and transient, but the most difficult part is the fact that you have very sharp gradient. So you have what we adopted is 3 different approaches to simulate these or to study this. The most costly, but the most detailed one is based on the finite element solver. And actually we use the Moose environment developed by Idaho National Lab because it has a very robust mesh adaptivity capability. We've also written what we call a steady state solver, which transforms these partial differential equation in ordinary differential equation. And finally, the analytical approximation that I'll describe. So what you have here is an example of a transient simulation that you can see the front propagates from left to right. There are some transient, but after a while, the front starts to propagate in a fairly stable fashion. And you can see a very sharp front for both the temperature, which is the yellow curve, and the degree of cure, which is the blue curve. And so the front propagates through the entire domain, just like it was in the experiment. Before validating this model, I want to also emphasize that this frontal polymerization takes place also in a gel. So this is a partially cured polymer, right? And so what you can see is that by introducing a thermal trigger with just a soldering iron, you can see that the front propagates to the part after you give it whatever shape you want, and then you end up with a fully polymerized part. So we can actually model this also using the model that the equations that I just described before. So in this case, the initial degree of cure is 20%, 0.2, and we can see that we also get a front that propagates. But what we observe numerically and experimentally, and this is that the front propagates slower when you propagate it in the gel, and it makes sense, right? Because some of the energy has already been used already. And so what you have here is a comparison between the simulation and the experiment for the front velocity as a function of the initial degree of cure. So the key contribution of our work has been to adapt it or to apply this to the manufacturing of thermoset composites. And so this is kind of an illustration of how we achieve this. We start from a carbon fabric. In this case, it's a 12-ply Toray T300 carbon fabric. And we start by the traditional process of vacuum-assisted resin transfer molding. So we basically infiltrate this fabric with the monomer, which is relatively straightforward because this monomer is not viscous. It has the same viscosity of water as water. But then after that, we introduce some thermal trigger by passing a current to a wire here. And then after an initial transient phase, we see that the front starts to propagate across the entire composite part. And so here's an actual video. This is an infrared picture taken from the top. So this is a 10 centimeter by 20 centimeter panel. And we start the process by running a current through the wire. And then we just turn it off and the front start to propagate completely on its own across the entire part. And we managed to make a panel like this, what would be out of an autoclave in about 2 minutes. And so here's what this panel is about. We made some larger panels. We made panels of different sizes. And then we actually look at the quality of the composite panel that we create by looking, for example, at the void volume fraction and observe that the void volume fraction remains very, very small, in this case, 0.2%. The fiber volume fraction for this particular process was about 50%. Now, if we want to apply it to very high performance type of applications, clearly we need to go to higher fiber volume fractions. And so instead of using the traditional double bag vacuum assisted resin transfer molding process, we actually adopt a Vartum, but under compaction. So that really allows us to reach higher levels or higher fiber volume fractions, all the way to 63. I think since then we've gone to even a bit higher. The void content remains very small, so it's still very good quality parts that we create. The front velocity, however, decreases as we increase the fiber volume fraction, which once again makes sense. And I'll come back to that a bit later. But obviously, the more fibers we have, the less resin and all the heat is associated with the exothermic reaction in the resin. So another approach, instead of going from, let's say, left to right, from one end to the other of the specimen, we can actually achieve this frontal polymerization from the bottom up by using the thermal trigger at the bottom of the specimen. And here's a part that we made fairly recently where the volume fraction is 65%, and the trigger is just run for about 15 seconds. Now, there's the infusion process, which took about 90 seconds. So the point is we can achieve very high quality composites much faster than the traditional way using this approach. Now, obviously, we want to emphasize the mechanical characterization of these. So we always compare the specimen that we manufacture using frontal polymerization, which are the middle bar, to those that we make using conventional cure, so using the manufacturer suggested cure process in an oven. And obviously, we also compare that with the traditional composite used in the aerospace industry, which is a carbon epoxy system. And so what we observe is that the properties, the darker bars correspond to the Young's modulus, the dash one or the pattern one correspond to the tensile strength. What we observe is the properties are relatively similar to those that we would obtain using a conventional process. They're not as good as what we would get with the carbon epoxy system. And one of the reasons is the fact that we've used carbon fibers that have been optimized for many, many years for a carbon epoxy application. So it's a different type of resin. And so we're looking now at improving the fiber matrix interface by using a new fiber surface treatment. And that's really important, right? The sizing of these fibers play a very important role in the strength of the material that we end up with. So coming back to the formulation that described the process itself, well, we basically extended the reaction-diffusion equation by just using a homogenized model. That's probably the simplest way that we can capture this. So now we have the same reaction-diffusion equation, except that now we use these homogenized properties for the thermal conductivity, the specific heat, and so on. And phi now is the quantity that describes the fiber volume fraction. So obviously we can, there are many different models to homogenize the thermal properties of composites. For unidirectional composites in the direction of the front, we can simply use a rule of mixture. But there are many more complex ones for different types of configurations and different types of propagation direction. But what I want to emphasize here is the key difference between the thermal conductivity of the resin and the thermal conductivity of carbon fibers. You can see there's almost 2 orders of magnitude difference between the two of them. And we expect that the difference will have a very important effect on the propagation of the front. And indeed, if you actually plot here the solution that you obtain for the neat resin, so in the absence of any fiber, 20% fibers and 40% fibers, we can see 2 things. First, as you increase the fiber volume fraction, the temperature tends to decrease. And it's expected, once again, because the fibers take some of the heat generated by the exothermic reaction. But also what we observe is that the front, which was the blue one, that was the neat resin case, the front seems to propagate faster when we go to 20% fiber volume fraction, and then a bit slower afterwards when we go to 40%. And that's obviously something that is important because the speed at which the front will propagate is a key component of the manufacturing process. And actually, we studied this both numerically, which are the red symbols. So this is the speed of the front as a function of the fiber volume fraction. And we also developed an analytical expression for this front speed as a function of the fiber volume fraction. And you can see a very good match between the two. And so what we observe is that it first increases, reaches a maximum, and then start to decrease, right? And this can be explained by just looking at the 2 equations that I just showed before. You can see that the increase is associated with the fact that the thermal conductivity, the homogenized thermal conductivity of composite is higher due to the fact that the carbon fibers are more conductive than the matrix. On the other hand, as you further increase the fiber volume fraction, we start to see a decay, and that's really associated with the fact that the source of heat that shows up in the second term over here has this 1 minus phi term in there, indicating that the more fibers you have, the less resin you have, and therefore the less source for this exothermic reaction. So we actually compare this with some experiments. The match is not bad in the sense that we capture the fact that it actually increases and then start to decrease as you increase the fiber volume fraction. And so we can also use this model to compare different types of reinforcement, whether you use carbon fibers or glass fibers. Glass fibers are less conductive than carbon fibers, so therefore we don't see this non-monotonic increase and then decrease of the speed of the front as a function of the fiber volume fraction, but we can see that it decays monotonically for the glass DCPD system. So This, by looking in more detail at these two equations that I mentioned, we can actually explore what we call the chemistry design space, right? So there are lots of parameters that show up in there, but if you actually perform a fairly straightforward non-dimensionalization of these equations and normalize the time by using this time constant A that shows up over here, normalizing the temperature by using the initial temperature and the temperature of the front, which is given by this, and normalizing the spatial coordinate using this particular length scale, we reduce these equations to non-dimensional form in which you have two parameters that appear. The two parameters that I denote by beta and gamma, the first one denotes the effect of the activation energy that shows up in the Arrhenius term, right? And the second one corresponds to the initial temperature of the resin. And so we can actually use this kind of approach to extract the full solution within the plane of these two non-dimensional parameters, beta and gamma, which are repeated right over here. You can actually plot the predicted speed of the front in millimeter per second. So DCPD has a value of beta of about 61, value of gamma about 1.3, would be right over here, has a speed of the front at about 1.5 millimeter per second. If I want to go faster, right, I want to go to the top left of this particular diagram. So that means two things. Either you can increase the temperature, right, and increase the value of gamma that you have over here, or you can, or you can decrease E, which is the activation energy. And so this approach allows us to study a wide range of possible chemistry that we have. We can also show that this particular approach, if we plot now the non-dimensional velocity, which is defined as follows, we can end up with a full solution that allows us to also look at the effect of the fiber volume fraction. So if phi is equal to 0, the velocity is about 1.5 millimeter per second. But as you increase the fiber volume fraction, you traverse this kind of space and obtain the speed of the front at different fiber volume fractions. So this is a very useful tool to really study different types of conditions. Let me finish by just showing 2 or 3 slides on another type of application of this particular approach, the frontal polymerization approach, which is based on 3D printing. The idea here is that we could use this approach to manufacture free-form objects of complex shapes. The idea is you can do 3D printing by having a colder gel that is kept at a fairly low temperature over here that is printed. And as the material is being printed, we have the front that just follows the printer process. And so that allows us to achieve these kind of situation where we can make, in this case, a relatively simple part, but it's a fully free-form, self-standing type of structure. You can see here that as soon as you deposit the gel, the front tends to follow the printing process and polymerize the material right on the spot. And that really allows us to achieve really unique forms, right? Free forms without the need of scaffolding or anything like this, and still achieve excellent mechanical properties. And so you can see at the end that you end up with a simple spring. Obviously, we can make more complicated shapes, and here are some examples that were made. So here's kind of a cantilever beam or very complicated, complex shape that we can make that is made off the ground completely. And obviously, the top one shows the more complex shapes that we can achieve with this particular approach. Now, these are for neat resin, but clearly we can add different reinforcements to these to the gel in order to achieve, or to the monomer, to achieve different types of material properties. We can add nanoparticles, nanofibers, and so on, to achieve different mechanical properties, thermal properties, electrical properties, and so on, for the types of part that we manufacture. So I will stop here. I will simply conclude that frontal polymerization constitutes a promising approach to manufacturing thermoset composite faster and for substantially less energy than conventional methods. We can capture this process by using the fairly classical homogenized reaction-diffusion equation or thermochemical model. Obviously, we can combine this also with a mechanical component, right? To capture the possible deformation of the process. The non-dimensional formulation reduces the model to just two key non-dimensional parameters, and this allows us allows for a rapid sweep of the different chemistries and or fiber content. And then it's also a promising way for the 3D printing of free-form objects with complex shapes. So for those who might be interested in learning more about it, I recommend the paper that we published in 2018 in Nature on this topic, and it gives a pretty good idea of some of the things that are possible there. There's also some supplemental information, so you can actually see some of the animations that I showed today. And with this, I will conclude. I put my contact information right here, and I want to once again thank the support of the Air Force Office of Scientific Research and the National Science Foundation. So with this, thank you very much for your attention.